Yeah, so today I'll be talking to you about a story that began more or less 70 years ago and how our work at CCB figures into this. Um, so, just to start with, yeah, good. Movies are playing. Um, in the developmental dynamics group, we study developmental biology and the quantitative problems that emerge from this. And one of the overarching problems in the field is, where does morphological information come from? And what does that mean? Well, it means that we, every one of us, started as a single cell, and we had to divide and turn into an amalgam of various cell types distributed in highly structured ways through space. And the question is, how do these cells know what kind of cells to be and where they're supposed to end up? And you can imagine different ways they can do this. You can imagine that it's all predetermined. We know genes exist. We know biological information is stored genetically in DNA strands. And you can imagine that if you were to decode the entire genome and fully understand it, there might be something like this that tells you every single individual piece of an organism and where it's supposed to go and the order which it's supposed to be assembled, and et cetera. On the other hand, you can have something, we know that complex patterns can self-organize, can emerge emergently. So, sand is not smart. Sand does not store information. Maybe in the form of a computer it does, as quartz, but certainly not here. And yet, through being driven by wind and through steric interactions between the particles, you get this complex multi-scale pattern that's emerged. So it's kind of an alpha and omega situation here. And this is a discussion that permeates a lot of developmental biology studies, both at the quantitative and experimental level. So when I said 70 years ago, I'm talking about this man who I think has affected all of our work one way or another. So Turing was interested in a particular problem. He was interested in how do regular repeating structures emerge in biology. And in particular, he's father of computer science, thinking about things algorithmically. He thinks, well, if you have a repeating structure, it doesn't really make sense that you would need to store a separate recipe for how to make each of these repeating structures and where each individual one is supposed to go. It makes much more sense if you, genetically store just how to make one petal on a flower or stripe on a zebra or digit in a hand, and then have some self-organizing mechanism that can place these repeated motifs throughout the body as developmental needs see fit. And so he set out to establish a quantitative theory as to why this happens. So he introduces this idea of morphogen, and this is actually great because this term morphogen actually stuck on even more widespread than his own theories. This is like arguably a major testament to his prescience, because the idea is that, well, there are chemicals called morphogens, and they're distributed throughout the body, and cells can sense the concentration of a morphogen at a given point. So a cell will know if there's a lot of a particular morphogen or very little of a particular morphogen, and the cell will make decisions based on this measurement. The cell will say, oh, yeah, there's a lot of this morphogen here. I'll adopt cell fate 1. I'll become this type of cell or do this behavior. And if the morphogen is not present, it will do something completely different, some other cell fate. And so Turing says this is a plausible way of understanding what could be happening to organize things, because we know genetic information is probably chemical in nature. This is about the time Watson and Crick is happening, so it's not known for sure what DNA is. But he has a good enough idea to propose this sort of underlying framework. And this transitions things from a problem about, almost philosophical problem about information to a more discrete problem, a mechanistic problem of how do you arrange chemicals in space in a reliable and periodic manner. So Turing starts thinking about reaction-diffusion, which is to say, he knows that chemicals will naturally diffuse through a domain. He knows that if you have multiple chemicals, multiple proteins, say, in a space, there's a ability of them to interact, to transmute from one form to another through reaction. Obviously, there are plenty of other ways you can redistribute chemicals, advection or active transport or other mechanisms we know about today. But these are two of the simplest mechanisms, and it's what he's thinking about and what we continue to think about in many respects. Turing's inspired by problems like phyllotaxis or other things where there are radial symmetries that are disrupted into some sort of dihedral symmetry. So he considers a very simple problem where you have a linear PDE, coupled PDE, on a ring that has linear reactions, linear diffusion, and this is an easy thing to analyze because, as we all know, we do just decompose it into its eigenmodes and study that to get linear stability. And it's great because he finds that if you choose your parameters correctly for your reaction rates and your diffusion constants, you can get a nice instability. So as common, the behavior of a given spatial mode in a linear system is determined by the signs of the real parts of its eigenvalues, of the eigenvalues of the Jacobian for that system. So he just plots it. He determines the dispersion relation, the growth rate for a given wave mode as a function of that wave number k. And for some finite set of wave numbers, you get positive growth rates, which is to say that if you perturb a system slightly about 0 or about its uniform state, that system will start growing, and it will start growing with some sort of spatial pattern. And this is kind of miraculous. It's kind of miraculous because if you actually consider what's going on, you're taking a system that's composed of a stable reaction. So one of the preconditions is the assumption that the reactions will just drive you to a stable, steady state when left to their own device. And you have diffusion, which is extremely stabilizing because diffusion damps out any kind of spatial heterogeneity for non-zero wave numbers. And both of these are stabilizing processes. And you put them together and you get something that is inherently unstable, inherently spatially heterogeneous. And this is kind of the brilliance of Turing in recognizing intuitively almost that this is a mechanism that can achieve self-organization in a biochemical system. Now, the linear system is more or less unphysical. You get negative concentrations at some values. That's obviously physically meaningless. Turing postulates this, which is a nonlinear reaction based on a very simple cooperative scheme. So the idea is, and it captures a lot of key features of what are later realized, including in our work, necessary for these kind of pattern-forming systems. So you have something injected into the system. There's a free energy that's being added in. Something's being converted at some rate to species X. X then converts to Y. Y that degrades. But there's a nonlinear cooperativity in the X to Y process. And through that nonlinearity, coupled with the constant injection of more X, you get patterns. Now, nonlinear PDEs are annoying. You have to usually use numerical methods to approach them. Turing had the best numerics available in his day, which is this pattern on the left, where he has an amazing 20 grid points that he runs to steady state. But he gets a pattern. He gets 4 spikes. And obviously, you can take the exact same system, run it a little bit better today. This is a 2D version of it. But this thing he came up with, this reaction-diffusion system, does give you nice patterns. They're actually very similar in their spatial distribution to, say, follicles, which is in skin in us, for example. So this is great. The one problem is Turing dies shortly after this. He never develops this idea further. DNA is discovered almost simultaneously. So people don't really think about biochemical pattern formation for another 20 years because the air gets sucked out of the room, so to speak. And this kind of key paradox in Turing's idea is somewhat left unresolved. What's the full mathematical understanding of how you get instability and what it means for there to be instability, and what are the kind of action items you can derive from this in terms of biology, let's say real biology as opposed to just equations. So 20 years after Turing, there's kind of a resurgence of interest in this problem from the mathematical community. You get these guys, Gear and Meinhardt, who do much more sophisticated numerical, taking advantage of a generation's worth of computational development, much more sophisticated studies of these reaction-diffusion systems. They're looking at it in 2D. They're looking at various parametric sweeps and looking at regions of stability. Simultaneous to this, Segel and Jackson are doing a full, linear stability analysis of reaction-diffusion systems and actually saying, okay, here are the conditions for instability. Here are the, relationships between the parameters. And between the two of these groups, they identify basically the key features that underlie all the stuff that's been done since. So if we look at the Jacobian for the linear system, right, or the linearized system in this case, key feature is the signs of the cross-diagonal terms have to be different. So this is a necessary condition, and you have that effectively this means that one species is going to be amplifying itself and the other, and the other species is going to be repressing both itself and the other. And the idea is that, well, absent any diffusion, this is supposed to be chemically stable. The repressor will just repress itself, but it will repress the activator so quickly the entire system damps out all fluctuation. So going to this kind of paradoxical diffusion-driven instability, what happens is, well, the necessary conditions become what you have over here. So we have that effectively the trace of the Jacobian, when k is equal to 0, has to be negative, so truly stable in that sense. But if this condition, the bottom condition holds, then you get, this is the necessary condition for there to be spatially non-uniform instabilities. And what this really translates to is a statement that D1 and D2 have to be sufficiently different from each other, by orders of magnitude often, such that this initially stable chemical process sees the fast diffusion damp out the repressor species so much faster than it can damp out the activator, that the activator has time to build up and self-reinforce and drive the instability of the whole system. And so this is basically the setting the stage for everything that's been done since. It's this idea that, okay, you need differential diffusivity in order to establish pattern formation in a Turing-style system. And so it's actually pretty amazing. Even though this was done in the 70s, it wasn't until the 90s, early 90s, that people actually managed to get one of these to work. So this is one of the very first studies where they had a synthetic Turing system. And it's actually beautiful. It's great patterns that they form. But it's extremely difficult because actually getting experimental systems where you have one particle and another particle, and they're moving around at extremely different rates in space, they're diffusing at extremely different speeds, is hard. And so this is true for biology too. So it took even longer. It took until basically the last, maybe 2006 is when they were able to finally find a single example in biology. And they found more since of chemical-based pattern formation as Turing and his successors envisioned it. And again, the reason is it's very challenging to get cells that move, or not cells, chemicals, morphogens moving slower than one another by an order of magnitude more when they're moving in the same medium, and often they're the same size particle. Practically speaking, this tends to happen. What you get is you get some particles binding to a large lipid or something, and that's slowing it down in these actually observed systems. But as Turing originally envisioned it, or as his successors envisioned it, differential diffusivity seems to be an exception rather than a norm for biological pattern formation. But this is only true in the way they imagined it. So let's imagine there's an easier way to get morphogens moving around at different speeds. And this is where our research comes in. So we're thinking about bulk surface processes. And this is more of an intracellular versus intercellular pattern forming process. But a lot of the same principles hold. So you can imagine a cell. And you can imagine just one chemical that's moving throughout the cell, say some protein of relevance to some signaling process. And that protein can be either in the bulk of the cell, floating around the cytosol, or it can be down to the surface, to the cell membrane. And, well, for a variety of reasons, when it's in the cytosol, the protein will move much faster, have a much higher diffusion constant than on the cell membrane. Because it's on the cell membrane, it's bound to the surface, it's having to interact with all the phospholipids there. Also, you just naturally want to move faster when you're diffusing in 3D than in 2D. So you have a much faster natural diffusion in 3D versus in the surface. Secondly, you can imagine that there's some nonlinear cooperative kinetics that affects the binding. So the more you want to bind, the more of a protein you have at a given spot on the cell membrane, the more protein wants to bind there. And it'll unbind at some constant rate, potentially, or some other nonlinear rate. But together, these are the ingredients for pattern formation that's more or less the exact same in spirit as Turing's original idea. The only difference is instead of it being some innate property of the molecules that leads them to diffuse faster or slower than each other. There's only one molecule, but it's still getting differential diffusivity out of geometry. So this is a very geometric-driven effect. And people recognize this. Oh yeah, I should mention this is a real effect as well. So two great examples. But cell polarization is a fundamental process. Basically, it's how cells know which direction they're facing. And so the idea of this is effectively that through the process I just described, proteins can bind to the surface. And as they bind to the surface, they form a pattern. It's effectively the simplest pattern you can possibly imagine, where there's just one high concentration region and one low concentration region, but it's a pattern nonetheless. And this is how cells orient themselves, how they basically decide which way is front, which way is back. And they use this to determine directions of motion or planes of division or all manner of other important things. It's a geometry sensing mechanism for cells in many respects. Happens in single cells, happens in multiple cell systems. So this is a C. elegans embryo. This is, right, is a mouse embryo with 8 cells, and each of the cells has the bright yellow region, like a high concentration cap that's formed on their outside, basically telling the cells which way faces outwards. So it's a widespread problem. And again, I want to highlight it's a very geometrical problem because in each of these cases, the polarization is communicating to cells a geometrical bit of information. And people have been thinking a lot about, like, okay, what's the actual relationship between cell geometry and the localization of these polar caps during polarization, the relationship between geometry and pattern formation. So these are some recent studies, and they all advanced hypotheses. So this one said that high concentration regions are attracted to high curvature. This one says it's an interface minimization process. So if you look at the interface between the high concentration and low concentration, you end up with whatever the minimum interface should be on that surface. A big limitation for these studies is it's just hard to understand like basic rules here. And the reason for that is because they're complicated. So in particular, these are a bunch of surfaces, and we simulated a bunch of different solutions to polarization reaction-diffusion system on these surfaces. And you look at it, you can see, well, if you look at the top, the proteins have oriented along the long axis of the cell. If you look at the right side, they're oriented also along the long axis, but they've achieved a different symmetry than the shape itself. So you've got on the left side a surface that has polarized to something that's basically an arrow. The other side, something that's effectively a dihedral symmetry. On the bottom side, you've got surfaces where the same surface can generate solutions with different symmetries, with very different just morphology. So a lot of things can go on non-trivially on these surfaces as you get to more complex and more complex geometries. And this makes it very difficult for us, because if we're looking at a model of this, what we want to actually do is to study a effectively nonlinear, non-local reaction-diffusion system on these surfaces. This is a hard problem to solve numerically and analytically. So the surface we're simulating in this is basically some reaction-diffusion system that exists on a uniformly non-symmetric surface. It's got some diffusion that's given by a Laplace-Beltrami operator. It's got some linear term that represents unbinding of a protein from the membrane. And it's got some sort of cooperative binding. So we have a local kinetics, this f of u term, which is just a Hill's function style, very common chemical nonlinearity. But this term on the right side, it's basically a term that's proportional in some way to the surface integral of the protein over the surface, the protein concentration. So what does this mean? It means that if you want to understand how this cell polarization process happens, you have to be able to both deal in nonlinearities and deal in the fact that there's a non-local effect, and this is caused by mass conservation actually, that's coupling all the points kind of non-locally to other points on the surface. So this is, as Turing would say, a very simplified model of a more complex system and a falsification therein. But it's kind of the most tractable way you can think about cell polarization mathematically. And even then, it's a hard model because it has, again, nonlinearity coupled with a non-locality on a non-symmetric surface. And, yep.
So that last term looks more like a penalty against changing the total mass rather than...
Exactly, yeah.
Okay.
Yeah, sorry if I misspoke. But yeah, so just to clarify, total masses in the bulk and in the surface are conserved, some of these. No new chemistry is being added to the system. This is very common in developmental context because you kind of end up with the proteins you start with before things can start synthesizing. And as we'll see, this is kind of what guides the formation of polar caps and sets the whole thing, acting the way it does. But yeah, big problem for this, and the big problem why all these previous studies didn't have more than hypotheses is because going into this, there weren't a lot of great solvers or numerical techniques for studying this kind of problem. Again, nonlinear, non-local, whatever, on a surface. This is why we got in touch with these guys from CCM, who have been really helpful in equipping us with the numerical tools needed to address this kind of problem. So they developed this double Fourier sphere method for approaching, at the very least, axisymmetric surfaces, and getting efficient numerical solutions of our equation on this class of problem. And basically, the way this works is you take your initial surface, you spread it out like you would a map, and then you doubly project it, so you have a top is reflected over the bottom, and this makes it much easier to decompose into decompose spectrally. You ignore the kind of common singularities of poles you normally have with respect to rotationally symmetric objects, and it's very fast. So the red line is the kind of off-the-shelf FEM I was initially using for simulations of this stuff. The blue line is Dan's code, and each of these grid points represents a kind of an increasing number of mesh nodes, so by a factor of 2 in each case. And what you can see really is just it vastly outperforms my FEM on both relative error and computation time. So this is really good because it means we can do some serious numerical studies on complicated surfaces without having to worry about, it taking, I think the initial code would take like an order of a month to run a really good simulation. So we don't have to worry about that anymore. Also, it looks very nice. So these are these polar solutions forming. And you can see the dynamics is very rich. So on some of these, it's just drift to the tip of the shape. In this middle one, there's actually kind of an Oswald ripening thing going on where two caps initially form and then one cannibalizes the other. Right side, again, it's some sort of drift on a torus. It's a much richer shape space that we can search, though, than these previous studies, which, again, we're looking at things like perlate spheroids and limited to that. Simultaneously, we're developing asymptotic approaches to study this problem. So this whole thing, again, differential diffusivity, lives in a regime where surface diffusion is very small. And because of that, we can asymptotically expand our equations in small delta, small diffusivity, and then understand what's going on, at least in this asymptotic limit, and use this to extract useful results about how the solutions look with respect to geometry. And so the first order timescale, the zeroth order dynamics rather, is entirely local in the sense that if delta goes to 0 in our initial equations, lateral diffusion drops out. That said, it's still fundamentally a non-local problem because of this mass conservation term that's tacked onto the right side. And so it's an odd sort of equation actually to study in the sense that, at least I found it odd. It's infinite dimensional system of ODEs that are coupled in this kind of mean field manner. So proving convergence to this was super obnoxious. We had to construct a Lyapunov function. We had to do a bunch of monotonicity arguments. But we can do that. And we show that, OK, on the short-term dynamics in the limit of differential diffusivity, what happens is you get the formation of an interface. You get some of the regions on the surface become high concentration, some become low concentration. And then once you have an interface, you can start thinking about how does that interface move. So this is the next order of the asymptotics. And basically, this is just your standard kind of Eikenall style, front moving at a uniform velocity, normal to its position, and nothing too exciting, except for the fact that we show that, asymptotically, the dynamics continue at this stage until the size of the domains, the size of the high concentration and low concentration domains, reach an initial or a final state that's strictly dependent on the kinetic parameters of the system. So first stage, again, you get asymptotically formation of interface. Second stage, the domains that had formed change as the interfaces move, and they change until you get some target surface concentration. Finally, at the last stage of the asymptotics, you get what's effectively a geodesic curvature flow on a surface that preserves that area domain. So having fixed your domain size, then you get, instead of motion that changes the domain size, you get motion that shrinks the interface locally while preserving that domain size. And this is what's most relevant to our kind of understanding of the system vis-a-vis geometry, because we want to say things about, again, how does the geometry affect the final states. Now we know that the final states are things that do in fact locally preserve the interface between high and low concentration regions. And we can start to try and pull results out, looking at things like the geodesic curvature, which has to be constant on these surfaces, and Gaussian curvature, which are intimately related. But I promise you we'd be combining numerics and asymptotics in this. So let's get to that quickly. Now that we've developed asymptotics, now that these guys have developed this numerical algorithm, we can start just validating everything. And so we can say, well, first thing, we got different time scales. We separated our time scales and found characteristic behaviors on each. So we can just run a bunch of simulations where we keep shrinking this asymptotic parameter delta and verify that everything we expect to scale scales as it does. And it does. We expect this first, this expansion phase to scale as delta to the -1. It does. We expect the geodesic curvature flow to move to converge basically roughly an order delta to the -2. It does. So this is all good. And we can actually kind of unpick this a little bit more just to verify. So what we did in this plot is vertical axis is effectively the interface length between the two regions. And the horizontal axis is time. And this is for a very small value of delta. So you get real separation between the time scales. And so what you see here is kind of up to t equals 10 to the 1, you get growth. The interfaces form, and as they form, just the total interface length reaches some peak. Then on the intermediate time scale, you see the interface length decays. And what's happening here is you go from some initial domain, we'll have a stick, to something instead where there is, going to this target area causes the size of the interface to shrink as you transition from that state to that state. So that's what we see. And then it levels off. It levels off for half a decade. And then it starts shrinking again on the next decade, and that's that geodesic curvature flow. As the interface shrinks, as these two polar domains kind of reorient themselves and merge and end up down at the final steady state. So this is nice. This is another thing that we really needed fast code for, because the simulation takes a very long time because we have to run at a very small delta and run a large number of time steps as a result at a high mass discretization. So not something that would have been possible easily with the FEM code we were using before. So now we can actually talk about some geometric results, ostensibly the whole point of this exercise. So to start with, just looking in the kind of broad literature on isoperimetric problems, on differential geometry, we can say a very simple result is known to be true and applies to our system, which is, well, we know we're looking for solutions with minimal interfaces. On spheroids, which are relatively simple shapes, these are the only two solutions that are going to occur at long time scales. So for the oblate spheroid, you're going to have, for the M&M, you're going to have some solution that's centered at the edge. And for the prolate spheroid, it's going to be something, football-shaped thing. You can have a solution that's centered at the tip and is axisymmetric in this case, and has some dihedral symmetry in that case. And this is definite. There are no other solutions we can conclusively say because of the great work of the field of differential geometry. What's also nice is just taking advantage of, again, known results in differential geometry. We can say we can construct surfaces that were hitherto unknown, where this model system produces a lot of non-trivial solutions. So this shape has negative Gaussian curvature, and it's incidentally also symmetric with respect to reflection about the horizontal axis, which is important because this class of shape then obeys certain rules that say that there are only so many constant geodesic curvature, that's to say minimal interfaces that can exist on that surface, and each class corresponds to a class of solution of our PDE, and so we've got this nice set of solutions where we have one that's just kind of a one-cap thing, very similar to the prolate spheroid, but then you get solutions that have multiple caps, or solutions where the high concentration or low concentration gets centered at negative curvature instead of positive curvature. And this is cool because it flies in the face of a lot of these intuitive prior existing results that had assumed things like only one cap can exist, because we know on flat surfaces only one cap can exist. The other caps will cannibalize and annihilate and merge into one cap. But we can show then surfaces, multiple caps can exist. Or this previous idea that maybe high concentration always goes to highest curvature. And we showed the opposite is true in this particular shape under these particular parameters. So this is nice because we were able to, again, combining numerics and asymptotics, produce a lot of unexpected results for what this system can actually do. The next thing we thought about was this question of robustness in biology. So I mentioned this system before. This is the 8-cell mouse embryo that always polarizes so that the high concentration goes on the outside of the cell. And these cells have really messy geometry. This is a cross-section provided by Hayden Nunley of one of these cells kind of imaged out from the rest. And I personally think it looks like a cheese wedge. But it's a little bit more complex than that. So this is basically a rounded top region, and then it converges to not quite a point, but it's sharp here. It's effectively a pyramid and ice cream cone type shape in some respect, but with sharp edges along the side. But the really interesting thing about this system, right, is it always polarizes to the outside of the surface. And one of the big open questions is what causes it to robustly polarize to where it's supposed to polarize. So we said, well, is geometry potentially playing a role in this? Because it could be geometry, it could be intercellular signaling, it could be all manner of mechanisms. We are concerned about geometry. So we said, well, we can take something that's, again, sharp on one side, blunt on the other side. This is just taking the qualitative, nature of what these cells look like. And if we run simulations, we see just, okay, there are steady state solutions that go to either side, either to the sharp or to the blunt side of these egg-shaped surfaces. But since we have fast code, we can just run a lot of simulations. We can say from 5,000 different random initial conditions, what fraction goes to one side versus another side, and how does this vary with respect to our parameters. So the horizontal axis on this plot, or the vertical axis on this plot, is basically how much goes to one side versus another side. This means that it always goes to the top. This means it always goes to the bottom. And what you can see here effectively is that for all the parameters we tested, and we've run a lot of simulations to get these error bars relatively small, it never really leaves the middle. There's some parametric dependence on which side's preferred. But again, these mouse embryo, they always polarize to the round side or more or less every single time. They have to, because that's how they know which side's out and which side's in. And so this says, well, geometry is probably not playing a pattern selection role in this system, which is interesting. And it's not something people were able to address, again, before having access to the kind of codes that can run a ton of simulations, ton of slow simulations on weird egg-shaped surfaces. So yeah, and then I'm going to talk about some future directions we're interested in. So everything we've done is axisymmetric surfaces thus far. But cells aren't limited to axisymmetric surfaces at all. Cells come in all kinds of bizarre shapes. So Dan's developed this code that can deal with now all manner of surfaces. So we're hoping to use that to kind of extend our analysis to more complex, potentially more realistic things like that weird cheese wedge of a cell I showed before. Second direction, more complex patterns. So this is a really fascinating, very important system that's getting a lot of attention right now in the last couple of years. It's min proteins. And unlike this thing I showed for the rest of this talk, this is a much more complex pattern. It's actually a wave pattern. So these are moving dynamically in time, as you can see by this chimer graph. But it's another intracellular pattern. It's another pattern that exists in a bulk surface type system where there are proteins binding to a surface, unbinding, and relying on that differential diffusivity to form these patterns. This particular study, which is very recent, is really highlighting that this is a geometrically dependent thing in very deep and not understood ways. So what they did right was they fed in this reaction to a controlled in vitro setup, and that controlled setup has a graded geometry. So as you move along this set of images, you go from thinner, thinner, thinner to thicker, thicker, thicker in terms of the bulk size, the dimension of the bulk. And you see there's a very sharp set of transitions between different styles of patterns. These are kind of more chaotic, more tightly packed patterns versus these classical like spiral waves that have formed over here. And this is, again, a geometric effect. There's nothing changing the chemical kinetics here.
Is this a gel with stuff in it, and you're looking at reactions in a gel? I'm not quite sure what the system actually is.
Oh, sure. So what they did is they have some way of binding it to the bottom surface. So it does this bulk surface process. They have some flow that's keeping things moving from the inlet through the bulk, but the idea is the bulk is still diffusing fast enough that it's relevant. And yeah, this is along the whole length of this setup, where these regions correspond to right here. These regions correspond to right here. And you get different patterns, effectively, because of the bulk versus surface kind of ratio. It's not fully understood, the details. This is a Irwin Frey paper, among other things. They're trying to understand it with this mass-conserved reaction-diffusion setup that they really like. But it's complicated, and they've only studied it on this extremely contrived, not shaped like a cell shape, which is why I think there's a lot of interesting angles for us to get into, because we can do real cell shapes, and we can look at these bulk surface systems that way. It's also just a very pretty system visually, which is pretty cool. And it's important for cells, because this is the min system. It's used basically for establishing in single cells midpoints. You have a wave that moves back and forth along the cell. It's a way to establish long axes in that cell. So this is a little bit of a contrived setup, but it's still a very interesting pattern formation. So finally, another kind of very interesting direction for things to move in is what happens when surfaces move. So there are two really good examples of what I mean by this. In a lot of these polarizing systems, you actually have a coupled cortical flow to the reaction diffusion. So you have a reaction-advection diffusion equation sort of setup. So in this case, right, you have one of these proteins is basically coupled with myosin recruitment. It triggers a surface flow, and this helps drive the pattern formation. So reaction-advection diffusion is one angle. The other angle, though, is just coupling to a, let's see if I can get this movie to play again. There we go. Coupling to a contractile surface. And when you have a deforming surface like this, all kinds of interesting features happen. You can get traveling waves of these polarized patterns where it naturally drifts. You can get a number of other really biologically relevant, but also mathematically interesting problems forming that are basically ununderstood and barely studied up until this point. Again, because these kind of simulations are difficult. So just in quick summary then. Effectively, we've studied this problem of cell polarization, and it's interesting because it's a much more widespread than the classical example way of diffusion-driven instabilities forming relevant roles in biochemical signaling mechanisms. We were able to work with our collaborators at CCM to get a set of new computational tools, which have been made publicly available, which really make studying this kind of problem much more interesting. Again, this problem being non-local, non-linear reaction diffusion on surfaces. Simultaneously, we developed an asymptotic study of this model system that enabled us to make a number of constructed specific examples that kind of yay or nayed various reigning intuitions about how these systems work and how geometry affects these systems. And finally, we discovered a bunch of non-trivial geometric effects, things people hadn't expected before, things people had expected but never been able to prove or even numerically verify. And so far, this has resulted in 2 papers, one dealing with the kind of numerical study and one dealing with the asymptotics, plus Dan's paper about the upcoming generic surface code. So just some acknowledgements quickly. We have Dan and Leslie from CCM, Cyril Murtop and Matteo Navaga, who were involved with the asymptotic study. Rocky, who did a lot of the early work on the spherical version of this problem in a prior paper, who's now at Duke, and of course Stas. And just as a last remark, it is the 70th anniversary of Turing's breakthrough paper. CCB is having a commemorative conference dealing with a lot of kind of current issues in self-organization in biology. And if anyone's interested in the kind of ideas we've been talking about in this talk, or just wants to see what biologists can provide to mathematicians and computer scientists as far as problems go, drop me a line if you want to attend or present a poster. We have free T-shirts. This guy's on them. They look great. So that's all.
We have time for questions, Pearson. I'll let you mail your own questions.
Okay. Yeah.
Yeah, thanks. This is really, really interesting. How much does does surface roughness matter at all here?
Well, this is a very coarse-grained model, so for us, no. More broadly, I don't think it especially matters in the sense that if you look at so let me go back to this slide, right? So this is the advection diffusion case, but let's assume that it's also the reaction diffusion stuff holds as well. This surface deforms a lot during the process of polarization, not like massively order the size of the cell, but maybe 1/10 the order of size of the cell. And polarization is robust throughout all of that.
Right.
And more broadly, if you take a cell, if you just press it with a pipette, that's not lightly press it with a pipette, mind you, then that won't change the polarization,
right,
especially, or at least the fact of the polarization happening.
Yeah, well, I was thinking of roughness on that scale anyway, like at the top image. So
yeah,
that makes sense, yeah.
So another example maybe is it doesn't matter enough to affect the assumption that a reaction diffusion equation holds. Reason I can say this is because system similar to this that I'm familiar with is rho GTP waves on the surface of a cell, and those are lightly contractile waves. So they, maybe locally contract the membrane, induce roughness on the order of 5%, but not enough that there's really discernible feedback of that roughness on the behavior of a wave.
Okay. Great, thank you.
Yeah. Oh, I can't quite hear you.
I don't know. Okay. Is it better?
A little bit, yeah.
Okay. So you mentioned that the double Fourier series is for axis symmetric, but it should work as is for non-axis symmetric also, right?
I'm not sure should. Can you explain that a little bit more? Maybe I'll pass this to Dan, who's in the audience. I don't know rather how for a non-axis symmetric case you get around the boundary conditions on the left and right side.
So it's a modeling question then, not a numerics issue.
It's a numerics question, yeah. But I'm going to pass this to Dan.
Yeah, I think it would still work, but you wouldn't get an optimal complexity elliptic PDE solver, I think, because in the axisymmetric case, the Fourier modes essentially decouple from each other. You could still do it, it just, I think, would not be optimal complexity anymore.
Sure.
Yep. Sure.
Okay. So in the beginning of your talk, you talked about instabilities. And so I wanted to ask you what exactly you mean by instability, because, for example, in my simple mind, a solution is unstable if it's growing exponentially, and if it's stable if it's decaying exponentially. But in your case, it's related more, seems to non-homogeneity.
Exactly
but it's not growing, like it's settling into something. So what is instability in this case?
So in this case, when we're talking about instability, we're talking specifically, exactly as you mean, in the linear case, things that can be growing or decaying exponentially. But we're talking in particular about whether the spatially inhomogeneous modes are the ones growing exponentially. So specifically, right, for something like this, even, the simple simulation, there's some initially uniform distribution of chemicals on this, right? Some concentration, two scalar fields. And you perturb it slightly with some spatially non-uniform perturbation. And if you imagine the linear modes that are around that uniform state, they're going to have different growth rates. And that growth rate is going to depend on their particular wave numbers, and it's going to depend on the chemical kinetics and diffusion constants. And when you're looking at a plot like this one, you can assign a growth rate to each of these modes. Those growth rates are going to be different. Some of those growth rates are going to be positive, which means those modes are going to grow exponentially. Some of them are going to be negative, so those modes are going to decay exponentially. But the ones that become finite from this infinitesimal perturbation are the ones that are going to lead to the formation of a pattern. Now, once you get to the sufficiently large modes, nonlinearities kick in. You're not going to have a sinusoidal mode, whatever. But it's all about, does the spatially inhomogeneous perturbation initially grow exponentially and form something finite and something that can become a pattern? I hope that answered the question.
On a certain time scale, like it's growing exponentially for some time, but then it settles into something else.
Yeah, exactly. Yep.
So this is So this is perhaps an unfair question. I wanted to ask about the bigger picture in light of your abstract. So you framed your talk in terms of the general problem of development.
Yes.
As posed by Turing and other people. So can you just say what's the present status of that? Because I mean the general problem of development goes far beyond just the existence of a Turing instability to the formation of more and more sophisticated patterns and so on.
Yes.
So how does the results that you presented change the way I, as an outsider, want to think about that?
Okay. So, like many things in development, this has a hierarchical answer. We have to look at it in terms of scales. If you want to talk about development as a whole, this initial question, that's complicated because there are a number of features. There's this whole pre-programmed, predetermined side of developmental biology, which I haven't touched on very much. But it turns out many of the developmental processes we have do need this exact programming. Mm-hmm. And so obviously, much of what I'm saying doesn't apply to that wing of things. That said, if we're talking about how this particular talk affects the idea of self-organization in biology, well, I think the important thing about this, if I want you to take away anything, is, as an outsider, is that there was this idea of differential diffusion. Yeah. And it was talked about by mathematicians for a while and sought after by biologists for a while. But it turns out they were looking in the wrong place. The most common form of differential diffusion, different pattern formation, isn't among tissues. It's among single cells, and it's this bulk surface process that's driving it. And it's fundamentally, as far as information is concerned, the information that's being passed down and created isn't a thing that's emerging out of, again, multiple chemical reactions interacting. It's a thing that's emerging out of one species of particle in a particular geometry that's telling it. So all these cases where geometry is guiding things, it's geometry that's telling the cell which way to align. It's geometry that's telling the cell which way is out. And so this is where we fit into the bigger problem. It's moving from a more localized view of what is and what isn't, say, morphogenetic information to incorporating broader ideas. And this is, I think, thematic of the field as a whole and where it's moving in terms of people thinking about geometric information, people thinking about mechanochemical instabilities and purely mechanical effects and how that leads to different fate outcomes. And then, yeah, I think that's 3 different kind of
Great.
length scales for you.
Thank you. And the related question is, just, speaking as a total outsider, it appears that part of the intellectual and technical accomplishment here is just solving in an efficient manner non-linear PDEs in non-trivial geometries.
Yeah.
And surely that must have application in a bunch of other domains.
Oh, absolutely.
Even outside the cell. Do you want to say just a few words about that?
So I don't have a slide for this, but for example, a very mappable system is just binary alloys, which is like a standard.
Yeah.
You can think of this as an Allen-Kahn type system where you have 2 alloys on a surface. And there's some very similar work, not with the same like kind of, I think, level of technicality as this work, but looking at just like self-assembly of binary alloys on colloidal surfaces.
Right.
A very related problem, like probably the most directly mappable. More broadly, plenty of people care about phase separating processes, which are again another interface-driven process, and how those apply to surfaces. So there's a lot of mathematical overlap with, I could list other problems, but like both in the realm of biology, but also outside of biology, that I'm aware of at least.
Right, and these techniques sound like they should be portable to those problems.
Oh, exactly, yeah. I mean, we're, in the initial numerics paper, we really tried to emphasize that, like, if you're interested in solving non-local PDEs on a surface, you really should think about what we're doing here.